Welcome back. Section 4.8 will close out our look at neutral geometry by looking for and not finding rectangles. We are going to look for and not find rectangles. To do that, we're going to need to take a look at angle sums. Now, for quadrilaterals, the magic number is 360. Now, coming up with 360, adding things to 360, that gets weird. So what we're going to look at instead is this idea of a defect. And the defect of triangle ABC is simply 180 degrees minus the sum of the angle measures. So when I say I'm looking for a triangle whose angle sum is 180 degrees, it's the same as me saying I'm looking for a triangle whose defect is 0. Similarly, the defect of some quadrilateral ABCD will be 360 degrees minus the sum of the angles of ABCD. So if I was looking for a quadrilateral whose angle sum was 360 degrees, that would be the same as me looking for a quadrilateral whose defect is 0. Okay, a couple of things that I'll want you to prove when we get together. And they are both labeled Theorem 1 because my copy pasting was terrible. My copy pasting was great. My editing was terrible. If ABC is a triangle and E is on segment BC, then the defect for triangle ABC is the defect of triangle ABE plus the defect of triangle ECA. That should almost be easy for you to prove. Secondly, if ABCD is a quadrilateral, then the defect of triangle ABC should equal the defect of triangle ACD. I don't think it'll be hard for you to prove either of those when we get together. Now, those matter because the following statements are equivalent. And you can read them. I don't need to read them to you. The thing that I'm going to do is I'm going to show that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 6, and then 6 implies 1, which means no matter what I'm looking to say, I can get to any other one in the list through logical equivalence. So that's the way we're going to do this. First things first, let's get 1 implies 2. If there is a triangle whose defect is 0, then there exists a right triangle whose defect is 0. So we'll take some triangle whose defect is 0. That triangle has an angle sum of 180 degrees. I want to show that there's a right triangle whose defect is 0. And so what I'm going to do is I'm going to drop a perpendicular right there. And I maintain that either right triangle that we just drew has a defect of 0 degrees. First things first, how do I know that that foot has to be in between those two endpoints? How do I know that D has to be between A and B? Well, let's pretend that A and B are acute angles. It's not hard to do that. Any triangle has at least 2 acute angles. We can rearrange vertices if we need to make sure that A and B are acute. If we were to extend ray BA, if we were to put D somewhere out here, if we were to draw the perpendicular out there, then we would have a right angle out here, which is greater than, no, not true, not true. The exterior angle theorem gets blown. Yes, an exterior angle has to be greater than the measure of any interior angle. So if we were to look at, pardon me, I needed a moment. If we were to look at this angle, whoa, I don't know what happened with that. If we were to, okay then. If we were to look at angle CAD, that's an exterior angle for this fancy schmancy triangle out here, and that exterior angle would be less in measure than that right angle right there. So we know that when we drop the perpendicular, it is happening in between A and B. Now that's fine. Defects add. The defect here plus the defect here is the defect of the whole thing. You proved that in the stuff we did. Well, you proved that in the stuff that we will have done when we get to talking about this in class. So if this triangle has a defect of 0. Defects are non-negative numbers. The only way to get two non-negative numbers that add to 0 is if both of the numbers we add are 0. So this right triangle has a defect of 0, and so does this one. And so 1 implies 2. Does 2 imply 3? If there is a right triangle whose defect is 0, does that mean there is a rectangle? Well, I don't think that's too hard. I think I can spin that right triangle around. I think I can spin that right triangle around. Take a good look. If I have triangle ABD congruent to triangle BAC, then this angle and that angle have to add up to 90. That's 90 already. This angle and this angle have to add up to 90. Defect is 0. So if I have a right triangle whose angles add up to 180 degrees, I can create a rectangle. Does 3 imply 4? If there is a rectangle, is there arbitrarily large rectangles? And the answer, stunningly, is yes. So I take some rectangle, and a rectangle, just so we're clear, is a quadrilateral with 4 right angles. It's a quadrilateral with 4 right angles. So here's what I'm going to do. I'm going to extend this all the way out here so that these are congruent. And I'm going to extend this all the way out there so that those are congruent. And I argue that AEFD is a rectangle. So just drawing a couple of segments here, just drawing what are basically the diagonals, some of the diagonals of the rectangles. I've got right angles here. I've got this congruent to itself. So triangle 1 is congruent to triangle 2. And it's not too hard to show that triangle 3 is congruent to triangle 4. And it's not hard to show that triangle 1 is congruent to triangle 3. And once that happens, you've got right angles here. You've got those add up to 90, so those add up to 90. You've got those add up to 90, so those add up to 90, and you get 90-degree angles all over the place. And so no matter how big my first rectangle is, I can make rectangles that are arbitrarily large by just stacking them one on top of another, on top of another, on top of another, on top of another. So 3 does imply 4. Does 4 imply 5? Does the fact that there are arbitrarily large rectangles mean that the defect of every right triangle is 0? And here's an interesting question. So I've got this right triangle, and I want to know if its defect is 0. So what I do is I create one of these arbitrarily large rectangles that I know exists. I know there has to be some rectangle where the length is bigger than CA, and the width is bigger than CB, that is an arbitrarily large rectangle. And I say, well, that arbitrarily large rectangle has a defect of 0, which means that if I draw this diagonal in, triangle DEF and triangle DFC both have defect of 0. That's great. So then I connect some more dots, and I say, well, that means this triangle BFD has defect 0, but more importantly, this triangle CBF has defect 0. And that's super, because triangle CBF is made up of the thing we want and this other thing with defect 0, and so this must have defect 0. So no matter what arbitrary right triangle I come up with, if there are arbitrarily large rectangles, then the defect of that particular right triangle is 0. Five to 6 should be fairly obvious. If I have a right triangle whose defect is 0, then any triangle has defect 0. You can divide the triangle into 2 right triangles. So the original, so no matter what triangle I have, I can divide it, no matter what triangle I have, I can divide it into 2 right triangles, both of which has defect 0. And then it should be fairly obvious that if every triangle has defect 0, then there is one whose defect is 0. This is a big deal because if you can draw a rectangle, then that implies that every single triangle has an angle sum of 180 degrees. Every single one. That is huge. And so you might say, there exists a rectangle is the same thing as saying Euclid's parallel postulate. And now we're back into yesterday's lesson. A couple of guys tried to create rectangles neutrally. One of them was Sakaki. Sakaki came up with his idea for a quadrilateral. He said, I'm going to take some quadrilateral A, B, C, D, and those are congruent, and those are right angles. Now in the Euclidean plane, that's a rectangle, but not in neutral geometry. Sakaki was able to prove a whole bunch of cool stuff. He was able to prove that the diagonals of his quadrilateral are congruent. That's not hard to do. He was able to prove that the summit angles are congruent. He was able to prove that ABCD is a parallelogram. That's not bad. He was able to prove that it's convex because it's a parallelogram. He was able to prove that the segment joining the midpoint of AB and the midpoint of CD, if you were to draw that segment in, it is perpendicular to both. And he was able to show that the summit angles, call them alpha and beta, must be either right or acute, can't be obtuse. But he was not able to show that they must be right. And so Sakaki failed in his attempt. I will ask you to prove some of those properties when we gather together in class. Lambert was the other guy. Lambert said, I'm going to try to make a quadrilateral, and it won't be too bad. I've got A, B, and I'm going to construct a perpendicular to C, and I'm going to construct a perpendicular to D. So right angle, and I'm even going to construct a perpendicular that way. And Lambert tried to show that alpha had to be 90 degrees. And Lambert was able to do some good work with his quadrilateral. Lambert was able to show that ABCD is a parallelogram, which isn't too hard to show, and therefore it's convex. He was able to show that BC is less than or equal to AD, and he was able to show that alpha is, he was able to show that alpha is less than or equal to 90 degrees, but he was not able to show that alpha was 90 degrees. And so he failed in his quest to find a rectangle. So I'll ask you to prove some of those properties when we gather in class tomorrow. Sakaki and Lambert tried so hard to come up with a rectangle, and they set it up in ways that we can do in neutral geometry, but they could not finish the job because if a rectangle were to exist, that would dictate that every triangle has zero defect, and if every triangle has zero defect, that's the Euclidean parallel postulate. So there, that's our look at quadrilaterals and neutral geometry in general. I will see you in class.